Good day, everyone. Welcome to ECE 45 Activity 2, which is the Silicon Run 1. My name is Evander C. Dago from BS ECE 48. So, here are the contents in this activity. The Silicon Run 1 consists of a summary or the summarization of what you have learned. Then the topics, discuss each topics that are presented in this video. First is the summary. Um, the integrated circuits in the computers that they navigate give an introduction to a new epoch in electronics. Each year faster, more influential computers are evoked, augmenting the ultimatum for a competent workforce and an intellectual public. Boosting understanding of manufacturing techniques in the semiconductor and computer initiatives is a scholastic challenge and one which is hampered by the casualty of visual imagery anticipated to the inaccessibility of industrial sites to students, educators, and the public. The Silicon Run two-part sequel addresses this scholastic challenge by taking hold of high-quality images of manufacturing on film or video to deliver a straightforward summarization of semiconductor and computer manufacturing. The Silicon Run 1, delivered in 1986, inquires into crystal augmentation, the impacts of doping, CMOS transistors in the composition and fabrication of IC wafers. The sequel is being employed for education and training. Thousands of students uh, universities, college, and technical schools are viewing these films or videos every year. The multiple modification in technology since the fulfillment of Silicon Run 1 make it essential to bring up to date the first film with the production of Silicon Run 1.2. The objectives of this scheme is to refilm the industrial manufacturing footage so the sequel can go on with equipping students with attainable information about today's manufacturing. Responses from the recipients of surveys overwhelmingly indicate that the sequel is an acquisition of undergraduate education. So next is the topics. The topics consist of time-lapse silicon crystal growth, wafer processing, design tools, CAD or CAA design, design specialist circuit design and layout, clean room procedure, mass fabrication, CMOS transistors, device animation, IC manufacturing processes. First is the silicon. Silicon is the most element found in sand, 20%, Earth's crust also second most abundant. The process is that the silicon is refined and purified as polysilicon chunks. Then it was heated into molten state. A small solid piece of single crystal is called seed is gently lowered into a rotated bath of molten silicon. The hot liquid silicon in contact with seed is cooled and solidified as gently pulled into molten region. After 48 hours of growth, the material is placed into a rotating machine to ground and from it into ingots. The ingot is cut into wafers through curved diamond edge plate grounding from both sides to attain smoothness and thickness from wafer to wafer. Rinse in edge to chemicals to remove contamination. The final polish is done only one side of the wafer. After from getting away from contamination, the wafer is measured for resistivity as a function of dopant concentration. Inspect package and sent to fabrication areas to be made into integrated circuits. Meanwhile, teams of engineers work together to design circuits into the surface of fabricated chips. Um, uh, Meanwhile, after that, computer architects work in highest level of abstraction to find overall function of chips. They establish microarchitecture, which regulates the timing and sequence of instructions. The telemicroprocessors. Each unit that was divided into different areas to perform specific function, designed by logic designer who works to a logic level to create more detailed specifications and establish hardware needs. Each unit is subdivided in corner of blocks which designed by circuit designer who works in transistor level. Design was made into interconnected switches known as transistors. These transistors was programmed by electronic communication engineers that perform series of logic ones or zeros, which is the main language of modern computers. To see how the transistor works, they examine the CMOS or complementary metal oxide semiconductors. N-channel transistors has two heavily doped electron-rich N-type regions, which called a source and drain become end of the electronic switch separated by P-type substrate, which is close to the gate. The source and drain is usually off. Applying small voltages create a net positive charge on gate, which turning the switch on, and when lit back to zero, the switch will become off again. While p-channel transistors, when normally off, is heavily doped p-type regions. uh, the separated lightly doped n-type substrate. Applying small negative voltage on the gate repels electrons but attracts positive carriers, which leads the switch to become on. It is possible to create both p-type and n-type transistors in the same wafer by doping section, known as CMOS, which acts as switch. A mask designer takes the circuit's schematic and manually lay out charm channels and each layers of mask generate masters blueprints. The naval engineers usually check the errors in this drawing, which is 4 or 500 times larger than aqua chips. Next, the information was electronically fed into computer in controlled beam machine. In ultra clean environment, final electron beam will etch the patterns into series of uh, chrome-plated glass plates. After it becomes masks that are used to transfer the circuit pattern into the wafer, then well checked and inspected to ensure good patterns. Then final were washed in acid before they are finally packaged. First, mass is heavily doped so that both type of channel substrate are exist on the same wafer, specified and electronically isolated uh, by growth of silicon dioxide. The gate R4 Mask 4 and 5 defines the drain region of the both type of channels. Next mask is the contact holes, which enables the aluminum wiring used to interconnect the individual transistors. Most of the transistors are masked 25 times depending on the complexity of the wafers. CMOS fabrication may involve hundreds of operations, including fully decontamination, fully gears, and fully equipped materials. Selection of type wafer with specific resistance are the main start of CMOS fabrication. All integrated circuits are fabricated using four fabrication techniques. One is the formation of the thin layers of silicon dioxide. Two is the introduction of dopant atoms. Three is the deposition of a variety of insulating and conductive materials. Four is the precision patterning of each three layers, but before the steps, a code is printed and recorded on each wafer. Starting in cleaning through acids in order to decontaminate from organic and metal contaminants, rinsing through ionic water and dried on nitrogen gas, Highly temperature is used in vertical furnace to grow silicon dioxide on the surface to protect from reaction. Pattern is applied on stencil through photolithography, then later put on photoresist. After several passes, the wafer will go to stepper, which undergo mask layer using ultraviolet light. There are also two types of photoresist, negative and positive, but resist is used, or the positive resist is used. Etching passes is still present, which can cause undercutting of photoresist that can create an exact transfer of mask. If, if critically fire etch, it undergo plasma etching. Hard resist removed by dry process using oxygen plasma, including fluorine, causes an insulation of the surface. Photolithography will be used and subsequently masked in the process, which allow isolate microscopic region of the wafer and construct the components of the circuit. Bombardment of wafers by dopant ions will create an n-type regions. Acceleration in high velocities on electromagnetic field and separation and other elements will cause ions to be driven on wafers, implanting silicon dioxide and blocks from unwanted region. Exposing to high temperature will penetrate down to silicon substrate. Silicon dioxide ground strictly monitored and measured. Silicon nitride deposited over dioxide layer in a deposition furnace. This prevents additional growth of dioxide layer and protects the regions where transistors are built. Another photoresist is done in order to prepare in the next mask. Each mask are perfectly aligned using computer. The next mask is used to define actual transistor regions, which is also exposed to cross the surface of the wafers. Wafers are developed to remove excess photoresist. Additional plasma etch on wafer are done in order photoresist to be removed. Then put again to silicon surface to grow field oxide reduces the electrical field with the insulation process and the underlying region, which blocks the current from leaking between devices, creating thousands of transistors. The remaining nitride layers is removed by any wet etching. Several process boron implanted on the wafers, resulting penetration of silicon substrate only on 10 thin layers. Silicon damage is removed and another layer of silicon dioxide is grown on the gate area. Silicon will be added on the surface using vertical furnace, which will dope of phosphorus. Photolithography is done on the next mask, then dry etch to create a gate. Remaining of photoresist is removed once again. After repeated masking and etching of silicon and boron, the wafers are already clean. The following is that thick insulating glass layer is deposited in order to cover the surface. The surface will chemical mechanical polish to create a flat reselection drawn patterns. On the next mask and photolithography is done in order to create wiring in the gate, drain, and source regions. Another mask is done to create holes, and tungsten metal is plugged in order to uh, ensure solid connections, then etch or polish down again. Aluminum silicon alloy is deposited to become first electrical wiring. Masking patterns the aluminum to form complex blocks in excess circuitry. Then aluminum removed using dry etching and photoresist is also removed. It leads to narrow metal strips, transforms from one transistor to another and becomes wires that connects the circuitry. After the desired levels of interconnection, in place, final layer of silicon dioxide is placed to protect the aluminum. On the last photolithography, only nitride are on the top are etched away, which is the contact points outside the circuit. The wafer is cut in photoresist and the run is complete. Finally, the wafers are ready for electrical testing and packaging. That's all. Thank you.